In this video, or these set of videos, we're going to talk about relational data with dplyr. Now, we've seen dplyr before as regular data manipulation type stuff, and data manipulation is a pretty big umbrella of what you can do or what you want to do with data, but something that wasn't under the umbrella of things that I talked about before is relational data. And relational data comes up a lot is when you have two or more data sets. So you can think of them as CSVs or tibbles, like tibbles inside of R, CSVs elsewhere, but you have information about various things. If you want to think of it, you can think of it as like a company having various data sets that each contain different information about different parts of a company or whatever. They contain separate information, but they share some common columns, some common values, and it is often the case that I want to combine two or more tibbles into one by that column. So I might want to smash data together, add some information to help inform my analysis, whatever that means. So I might have anyway, I won't go through too many examples because I have some in the slides, but here's what we're going to look at. So intro to relational data, and then we're going to look at a couple different types of joins. So mutating joins, filtering joins, set operations, and then there's a last part, a new part that I just added that I haven't talked about before. So we're debuting it here, and those are non-equid joins, and we'll talk about what that means probably in a separate video, but we'll get there. So in general, what is relational data? Well, I already sort of introduced that, but it's multiple tables of data that share some common variables or attributes. Okay, and so I might have a company that has information, a list of people who've bought from them before, a list of the transactions. So they might have just like a customer list separate. They might have a list of transactions that are separate, and then they might have a list of products, again, separate. I can smash those all together. So a transaction, so of course, the customer will probably be given an ID when they make a purchase, or they make an account to make a purchase. And so there's a separate data set that has the name of the customer maybe and the ID that was created for them when they signed up. And then you have a separate CSV, tibble, whatever. Okay, that data set's going to be long because you have a lot of customers, but what's even going to be longer is a list of all the transactions that you've ever had in, rolling time. And so if I want to analyze customer behavior, I might want to combine them and have the customer name along with each of the purchases. And then I could add in a third data set that is like, what part of the company did they purchase? Who knows? Okay, so I won't get too far gone with my example. So now, there is a number of different vocabulary terms about relational data that we're going to work with a lot, so I have to introduce them here. So, a relation. The relation here is not important, not the individual data sets. So, a relation will always be between a pair of tables. Subsequent relations will build off relations of pairs. Okay, it is. I'm sure it's clear as mud at the moment what I mean, but we'll get there, I promise. Okay, and so the verbs we're going to work with between these pair of tables. So basically, I guess before I get ahead of myself, I've said that about 5 times now and always gotten ahead of myself, but we'll keep trying. A relation is the variable that exists in both of the data sets. Okay, so they are joined or related in some sense, and that's what we really care about. That's what we have to define, and so on and so forth as we get there. Okay, and so the verbs that we're going to use with mutate, filtering, set operations, and I said also non-equijoins. So as an example, so I'm going to use this example. We'll go over this, and then I have an R file that I've created that I will show and then give you about NYC flights in 2013. So it's a data set it's a package in R that contains a bunch of data sets, 5 to be exact, about all the information about flights going to and coming from New York City. Okay. And so there are 5 different data sets. So airports, planes, flights, weather, and airlines. Okay. 5 different data sets that each hold different pieces of information, but they are paired in some sense. And so you can see those pairs in this sort of infographic thing that flights is the main one that keeps track of every flight that came in or out of the airports in New York City. But, of course, I might want some information on weather, how did that affect the flight, so on and so forth, what specific plane it was, what airline, so on and so forth. And so you see these various relations between the data, and that's what's important. So we'll come back to NYC flights in a little bit. So the important thing about relations are keys. So the variables that we use to connect the data sets are keys. There are 3 types of keys: a primary key, a foreign key, and then a surrogate key. So a primary key uniquely identifies an observation in its own table. You always think of, I have 2 tables, like a left and a right. And so there's always like a first and a second I looked with. A primary key uniquely identifies an observation in its own table. A foreign key uniquely identifies an observation in another table. Okay, a variable can be both a primary and a foreign key. What that means is that if I have a variable named x in dataset A and a variable named x in dataset B, and they are a relation, that can be x can be both the primary and the foreign key. Okay. So and then we have a surrogate key, a key that's created because the dataset lacks a primary key. So I could create just an ID for each row. So it lacks a key. So and I have a data set that's 500 rows. So I could just make I could mutate, and I could make another variable, and that variable is just like 1 to 500, and that might be a key. Okay. So a primary key and the corresponding foreign key in another table form that relation, like I was saying before. Okay, so mutating joins. As a setup, I have 2 data sets here that I'm going to work with. Very small, very simple data sets. And I will vary the data sets as we go. Okay. But I have these 2 data sets, and I want to do stuff with them. So I'll call them dataset X and dataset Y. I'm using a special function here called a tribble, which allows you to sort of write the data frame as you go. Also, if you are a Star Trek fan, you might people get excited when they see tribbles because there's an episode, I believe, called "The Trouble with Tribbles." So I don't know, if you need some extra excitement and you are a Star Trek fan, there you go. And so I have these two data sets, and I want to join them. And so what we're going to use, a join is a way of connecting the rows in X to 0, 1, or more rows in Y. And so I'm going to have this graphic down here. I did not create the graphic. This is from our book, R for Data Science. And so in no way can I take any credit for making these very good graphics, but hopefully they'll be helpful. Okay, and so we're going to go through these different joins and see how they would react, or how they would act, not react. Okay, and so we have a couple different ones. We'll start with inner join. So as usual, the names of the functions are very much meant to mean something, um, and they'll always follow the same path, so to speak. It's going to be the first inner underscore join. So star underscore join. Then of course the first word is going to tell us how the join acts. So inner join matches pairs of observations whenever their keys are equal and drops everything else. Okay, so um, if it exists, it goes through X, and if it exists in Y, if it has a partner that exists in Y, it stays and gets smushed together. And if it doesn't, it gets thrown away. So we have 1, 2, 3. So the first, you can look at the like each data set has two columns. The first column are going to be the keys, and so it's the 1, 2, and 3, not x1, x2, x3, or y1, y2, y3. Okay, so we look in the data set to the left, and we're trying to match it to the data set to the right, and we're seeing does 1 has a match, 2 has a match, and 3 does not have a match. And then we look in the right table, and 4 does also not have a match in the left table. And so 3 and 4 get dropped. So that's inner join. Okay, and so inner join looks like this. You can do it either way. So I put it here as sort of naturally the function, or you can, of course, pipe something into a join. Remember that pipe, whether it looks like this or it looks like the one I use, takes the argument to the left of the pipe and plugs it into the first argument in the function to the right of it. Okay, so that's inner join. Now there are a few different outer joins: left join, right join, and full join. Okay, so left join keeps all the observations in X, right join keeps all the observations in Y, and full join keeps all of the observations in both. Left join and right join are basically the same. So if you weren't happy with your right join, then you just change to the left join, and you'd keep X, whether you're keeping X or you're keeping Y, and left or right, you can match up to make sure it's what you want. So generally, most people use left join. I don't see a lot of people using right join, but it is there. It does exist. Okay, and so this is what that would look like. So left join, in the left join, all of the observations in the left one stay. Okay, and you're sort of matching it to the right. So you look going down the row. Does 1 have a match in the second? So does Y also have a 1? X has a 1. Does Y have a 1? Yes. Let's match them. So then 2. Does 2 have a match in Y? Yes, there is a match. So we'll match them. 3. Does 3 have a match in Y? No, it doesn't, but it still stays, and you add an NA, okay, which can be annoying, but may be what you want. You may be trying to find what doesn't have a match. Actually, there's a better way to do that, but it's one way to do something like this. Okay, so 4 drops because I'm not checking to see if it has one. It's in the secondary data set that only is there to be matched, to check if it has a match. Yeah. Okay. So that's left join. Right join, you see very similar, except now I'm keeping 4 and seeing if it has a match. It doesn't, but of course it stays, and 3 drops because it was in the left data set, and I'm using right to join. Okay. And then full join, it's going to keep everything. Okay. If it has a match, it's going to match it. If it doesn't have a match, it's still going to stay, but it's going to get an NA. Okay, so those are the mutating joins. Okay. Now, what if I have duplicate keys when the keys aren't unique, which means there's more than one? Well, as you can see here, 1 and 2 in the left data set. And so what happens is it matches to both of them. Okay, you get all possible combinations. So when you have duplicate keys, you get all possible combinations. Okay, And so you see that here. Okay, and now we get to defining the key columns. And so there are multiple ways of doing this. And actually, there's a new way that I'm going to stress at the end of this slide that just came about in early 2023. So they released something, they released an update of dplyr that did a lot of new stuff and a lot of work on the non-equijoins, which we'll talk about in a little bit. Okay, but there are multiple ways of defining a key column. And so you can just not do it. Okay, by equals null, which is the same as not putting anything there. And if you do that, that's called a natural join. And so it's going to use all of the variables that have a combination, so that exist in the two data sets, which can be just one variable or it can be many variables. So that's called a natural join. Okay, by equals x. So you can do it by a character vector, but only uses only variables defined in the key. Or you can do something like this, a named character vector. So that first one would only work if x existed in both the first dataset and the second dataset. And then here, third, this is a case where I have, it's called something different in the two datasets. So in my first dataset, it's called A. In my second dataset, it's called B. That's how I want to match. And then I get to the new one. The new one looks like this. Okay. The third one down, the by equals, and then I make a vector C A is B, is kind of, well, is clunky, or people defined it as clunky. And so they came up with this new, what we'll call a helper function. And the helper function is named join underscore by. And so if I take that third one, which is sort of the old way of doing it, and then we make the new way of doing it in line 4, you can see join by, and then A is in the first one, B is in the second one, and I want to say that they are equal to each other, which we'll see is not always the case, but it gets us the join we want and helps us, or at least the authors hope that it helps you express the joins more naturally. And so I'm going to stop here just as a sort of natural stopping place to not make our video go too long. And we'll pick up and finish joins in the next video.